You wait. I had some technical issues, so it took some time. I hope you can see me and hear me loud and clear. Welcome aboard. Hi Ramya, Ankit, Shyam, Kalai, Moria. Welcome Tejas. Hello everyone. This is Shreyas here, your captain. And today's session is lecture number 3 of Re-Optics for all the 12th standard and the dropper student. It is a part of the Pathfinder series. And today it's all about refraction at plane surfaces. There are amazing phenomena which are related to refraction. You might have heard about mirages. You might have heard about a phenomena called as looming. You might have heard about optical fibers. There are so many things in our day-to-day life and also in the form of applications for different scientific and technological aspects where refraction is used. We are going to solve some amazing questions today on refraction, the bending of light, speed of light, how it gets affected, and also glass slabs. All of this in today's session with me, your physics master teacher at Vedantu. Hello, hello, hello. Welcome aboard. Hello unknown. Hello Gaurav. Welcome all my lovely warriors. This is lecture number 3, refraction. This is what we are going to cover today in case you want to know about it. Yes. And those of you who do not know me, this is Shreyas here, your captain, your master teacher for physics at Vedantu. And I have started a very interesting thing on Instagram. So you might want to note that down. And I'm going to keep daily quizzes on my Instagram account. All right, so you're going to have lots and lots of quizzes. And you're going to see the answers and some interesting facts every now and then on my Instagram account. So that's the reason why you should check out my status every now and then. Lots of fun things that you will get to know in the next few days. Also, some special things coming on YouTube from my side, you will get to know very soon. So that's about that. And yes, if you love my videos, if you enjoy watching this channel and you want to support this channel, go ahead, smash the like button and also hit the subscribe button, because this is one of the unique kind of channel where, not just that this is in English medium, but we give you everything that you need for 11th, 12th droppers with revision, mock test, full syllabus course and what not. All right, so let's get moving. So Miss Abhirami, my Telegram ID, actually I'm not so active on Telegram. Apart from, the groups, I am not so much active on Telegram, so it will not be so much of use even if I give my Telegram ID. It's better you can install Instagram and you can just probably use that Instagram just to, ask anything that you want to me. All right, so let's get moving. Thank you, Devendra. Yep. Yes, I will also upload the quizzes in Telegram. Yes, that's a good idea. Abhirami, I'll do that. Definitely. All right. Ankit, there is little bit of theory, but lots of problems for sure. All right. Hello. Welcome. And guys, if you want to cover up your syllabus, maybe the 11th and the 12th, all of them, and maybe you have covered the syllabus, you want quick revision, and maybe you want assignments, you want more problems, and maybe you want to attempt more mock tests, and maybe you want to just compare yourself with the current crowd who is going to give the examination, then remember there is a crash course which is running right now for the 12th as well as the dropper students. It's available at 10% off using my coupon code SHHPRO, and you get it for 9,000 rupees. That's less than 100 rupees per session. So go ahead, check out the link which is there in the description box in case you want to push yourself in the last few weeks just before the run-up to the JEE Mains examination. Now, you might have all heard about refraction, and you might have all heard, seen videos, or maybe even tried it out at home, keeping a pen in a bucket or a jar or a beaker of water. And you see that the pen appears to be bent, broken, and that is just a notion that you get. Actually, the pen is not bent or broken. It's just because the light bends, you feel that the pen has bent or that straight object has, been twisted. But actually speaking, nothing like that has happened. It's just the way the light ray travels. It's a very good example of showcasing that the light bends when the medium changes. Usually, light travels in a straight line. Everybody would have heard about this. Light travels in a straight line. But the moment the medium changes, then there is a good chance that the light will bend. And how it bends, what are the laws, we are going to see that and lots of optical problems today. You can even try this at home with a simple protractor, with probably a laser beam. You might have seen that in some fancy stores, or maybe in some fun fair or something. You take a laser, and if you have a glass piece, just try to point that laser at different angles. You will see the light ray will bend, and if you see the relationship, it's very, very interesting. But before that, we are going to see some more properties of the bending of light and refraction. So this light, all right, so when it changes medium, like I said, the speed, when the medium changes, the light will bend. It may not travel in a straight line, and the light which is falling on from the first medium is called as the incident ray, and the light which passes into the other medium is called as the refracted ray. Refracted ray is the ray which passes on to the other medium. I stands for the angle of incidence. This should be kept in mind. Incident angle is always measured from the normal drawn. You always measure the incident angle from the normal drawn, and refracted angle R. This R stands for your refracted angle. This is your refracted angle, and obviously this I stands for incident angle. They are all measured from the normal, just like in reflection, as simple as that. Now, a very interesting phenomena which occurs because of refraction is what we are going to see today towards the end of the class. If you are a bird, I know you are not a bird, you are a human, but if you are a bird and you look at a fish, you will feel that the fish is very close to the water. And if you try to catch the fish, if you have ever tried to catch the fish by your bare hands, just by the look of it, it will slip, not because you are slow or the fish is fast alone, but because you feel that the fish is here, but actually the fish is much deeper than what it seems to be. Yes, that's what happens. And that's why most likely you're going to miss catching that fish. And you will see why this is happening is because the rays of light which are coming out from the fish are getting bent when the medium changes. Water, air. The medium has changed, the light rays have bent. You feel that the fish is somewhere else. Apparent notion. All of this you're going to study today. Now, remember, we define a property. We define, oh, Ankit has already tried this. Very good. Thank you, Devendra. Now, here is the thing. See, before even we go to Snell's law, I know everybody's like, sir, where is Snell's law? Sir, where are those problems? Hold on. There are a lot of things. See, very important thing to note, apart from the light bending, the second thing which changes is the speed of light. All of you might have heard, light travels at the same speed, and that is 3 lakh kilometers per second. But the moment the medium changes, then the speed of light will also change. And speed of light is highest ever recorded in vacuum. You cannot make the light go faster than 3 lakh kilometers per second, no matter what you do. That's the fastest thing, and that's in empty space, that's vacuum. Any other medium that the light enters, the speed reduces. And the factor by which it reduces, that defines a property called as the refractive index of the medium. For example, I tell you the refractive index of a medium is 2. That means when the light ray will enter from vacuum or air into that medium whose refractive index is 2, if the speed of light was 3 lakh kilometers per second, which is 3 into 10 to the power 8 meters per second, after it enters that medium, it will become 3 into 10 to the power 8 divided by 2. So that factor is called as the refractive index of such material. Is that clear, my warriors? Yes, Ramya, next class is again tomorrow. Okay. Kamal Raj, which book you should follow for physics apart from H.C. Verma? Yes, like Ankit said, I.E. Rodo is there. You also have D.C. Pandey. You have, Tattva material. You have PYQ, either from Disha or from Arihant. These are the good books that you can follow. Perfecto. Perfecto. So that factor is called as the refractive index. So that's what I'm going to put over here. So mu is the symbol for that. Mu is the symbol for that. And that is speed of light divided by the speed in that medium. So you will see this V is always less. Think about it. This is always less. This is always more. So mu of any medium is always, this mu is always going to be more than 1. This is a property of the medium. This is the property of that particular medium. And this is sometimes also called as the absolute refractive index. This is called as the absolute refractive index. But there is a term called as relative refractive index, meaning when light goes from, not from vacuum to, let's say, water, but let's say water to glass, or maybe some plastic to some other material, then there is a comparison, and that comparison is via relative refractive index. This is absolute refractive index. So what is relative refractive index? Let me just put it over here. Okay, let me just put it over here so that you get a sense of it. So, all right, so let me just put it. All right. So, relative refractive index is written down something like this. Let's say the light goes from medium, the light goes from medium 1 into the medium, light goes from medium 1 into medium 2. Then I will write it down like this: refractive index of 2 with respect to 1. Because it is going from 1 to 2, you will write it as refractive index of 2 with respect to 1. Since it is going from 1 to 2, you will write it like this: 1 mu 2. This is how you will write it. The light is going from medium 1 to 2, but while saying it, you will not say refractive index of 1 with respect to 2. While saying it, you will say it is refractive index of 2 with respect to 1. That's the only confusion which happens. This is the only thing which you should be careful about. So this is relative refractive index when light is going from one medium to the other medium, and it turns out to be, okay, it turns out to be nothing but mu 2 by mu 1. Mu 2 by mu 1. As simple as that. Yes, it is always going to be more than 1. Yes, it is always going to be more than 1. Mu is always going to be, absolute refractive index will be always more than 1. Relative can be less more than 1. Yep, I hope. Why do we say like that? I don't know. It's just historical. That's it. Yeah, it's just historical. Oh, Aman, even if you are a student of 9th, definitely you can watch it. And Kalai, I would definitely not recommend Cengage, although collection of problems is good, but I have not seen much use of Cengage. So I would tend to avoid Cengage. If you have DC Pandey, Arihant, Tattva, H.C. Verma, Erodov, these are good books. Okay, fair enough. Now, also remember this mu 2 and mu 1. Think about it. From this definition, these are absolute refractive indices. These are absolute refractive indices. So this will be C by V2, and this mu 1 will be C divided by V1. So basically, what will this come out to be? V1 by V2. So remember, 1 mu 2 is nothing but V1 by V2, but it is mu 2 by mu 1. Interesting, confusing. Okay, it takes some time for you to get used to it, but with time, you'll for sure understand this and remember this as well. So you need to remember this formula for sure. Even if you don't remember this, it's okay, because you can get this directly from over here. So I'm going to block this as well. I'm going to block this as well. Very, very important formulas. Now, last thing before we go ahead, very important formula again coming up on your screen. Remember this one more formula. 1 mu 2 is nothing but mu 2 by mu 1, and 2 mu 1 will be nothing but mu 1 by mu 2, correct? 1 mu 2 will be mu 2 by mu 1. 2 mu 1 will be mu 1 by mu 2. That means they are reciprocals of each other. Therefore, 1 mu 2 will be 1 upon 2 mu 1. So when you change the order, when you change the way in which it is traveling, if you reverse it, then the refractive indices are reciprocal of each other. Okay, 1 mu 2 is reciprocal of 2 mu 1. I had seen, once a student, what he had done. He had done this. somebody had asked, what is the refractive index of the glass with respect to water? He remembered relative velocity and he wrote, oh, relative velocity V1 minus V2. So he wrote, it is nothing but mu G minus mu W. This is completely wrong. Okay, this is not correct, guys. You cannot subtract refractive indices like that. They multiply, divide like that. Okay, so you need to be very careful. You cannot just subtract them just like you did it in relative velocity. Is that okay, my warriors? And avoid this silly mistake. Have you written it down? SL Arora for JEE? Yes, it is a good book for JEE Advanced Plus and Olympiads. If you want to target Olympiads, yes, then it's a good book. Daneshwar. Yeah, alrighty. Perfecto. Let's move on to the next one. I hope this is all there, and don't worry, all of this is going to be there in your notes in the PDF when you download the Telegram group. I have put the refractive indices, absolute ones, on your screen. You don't have to remember it. It's just to get you an idea. For air, it is not 1, it is very, very close to 1. 1.00, 3 zeros and 3. It's almost 1. It's like vacuum. Ice, water, all these things, like 1.33, 1.34 and so on and so forth. For crystals like quartz, it's 1.46. Glass, it is close to 1.5. Diamond has very good refractive index. It's 2.42, very high refractive index. You can see that. Okay, it's just to give you an idea of how refractive indices are around. So that if you get some refractive index, like somebody will get it as 200, then you should think something has gone wrong, because the refractive index won't be 200 or 300. Okay, fair enough. Now that we have spoken about, how the speed of light changes, and how to calculate relative refractive index. Remember, light is a wave. And what does a wave have? It has wavelength, it has frequency. So you might have often wondered, sir, if light goes from one medium to other, the speed changes. But what about frequency? What about wavelength? Does that also change? Think. Let's say you have some color of light, or some light of certain frequency and certain wavelength. It's traveling in air and it enters water. What will happen? Speed will change for sure. Frequency and wavelength, what will happen to that? Put it up in the chat box. Oh no, Ankit, you don't have to remember these values. Abhishek, both are good. It depends on what you want to do. If you want to do research, go for IIT. But if you want to do engineering and all of that, yes, then go for IIT. Frequency remains the same. Oh no, Sham, frequency remains the same. Frequency is only dependent on the source. I'll repeat over here and I'll put it right over here. Just one second. Okay. Yes. So remember one thing. Speed of any wave, this is for any wave, it is always dependent on the medium. The frequency of any wave is always dependent on the source. And speed of any wave is f into lambda. So once speed and frequency are decided, this lambda is decided in the end. So lambda depends, it depends on frequency and the wave speed. Remember, this is always this particular flow. Always start with speed, frequency, and then you go to the wavelength. Many students always get confused. Sir, if this changes, wavelength changes, then will frequency change or will speed change? See what is same, what is different. Now, the source of light was the same. Light came from some source. It changed the medium, but the source of light is the same. The frequency will remain same. Speed changed, so what will change? Wavelength will change. Understood, my warriors? Yep, the wavelength will change. So this is what happens. Now, when light goes from one medium to the other medium, you will see the wavelength will change. Look at this, the wavelength is changing. Very, very interesting diagram. This diagram should be embedded in your memory. This is why I have put up this simulation exactly for you, so that this enters your head and you will never make that mistake. Look at the speed, the wave speed is large. Here the speed has decreased, it has become slow. Now, if V decreases, lambda will decrease. If V decreases, lambda will decrease. So that's why wavelength has decreased. If speed increases, wavelength will increase. Is that okay? I hope this is clear. Yes, this was also told in waves. And this is a generic property of waves. This whatever I have given over here, this is a generic property, not just for light. It is also applicable for sound waves, electromagnetic waves, any waves. This is always true. Fair enough. Yep. Great. Moving on to the next one. Coming up on your screen is a question. Let's see if you guys are geared up for solving this question. Oh, by the way, I don't know whether you noticed, I've changed the color theme a little bit. You know, so much of work went today. I've changed the font size. I've pushed the options a little bit towards that side. All the things are on the top and you can see the font sizes are different. I took your feedback. I've also changed the background color over here. Even that, the symbols and the icons are a little bit smaller so that we get more space to work around. So all of this in the last one day. Okay, so thanks to the content team and thanks to all the people behind this who put in all their sincere effort to making this, convenient and easy on the eyes of all the JEE enthusiasts, all my lovely warrior army. Thank you. Thank you so much. All right. So the ratio of the thickness of the of the plates of two transparent medium A and B is 6:4. The light takes equal time in passing through them. The refractive index of B with respect to A. Acha. Thank you guys. Thank you guys. You loved it. I can see that. Thank you. So let's try this out. Okay. The ratio of the thickness of the plates, but what is same? Time is same. Now imagine this is a slab. Okay. This is the thickness. This is the thickness. And let's say the thickness is D. Okay. This thickness is D. Then the light which is going to travel in this with some speed, it will take some time to go from one end to the other. That time will be distance by speed. Distance by speed, correct? Now, speed, we know, will be different in different slabs because the medium is different. So, if the medium over here has a refractive index mu, can I not say that V will be nothing but C divided by mu? Therefore, it will just become D by C into mu is equal to time. Fair enough, my warriors? Everybody agrees to this? All have done is speed is nothing but C divided by mu. That's what we have seen. Great. Now, think time is same. Thickness of the slab is different. Speed of light is constant in vacuum. C is a constant. Mu is different. So, D into mu is a constant. Do you guys agree? Therefore, D into mu will be a constant for both of them. Since, why is this true? Because T and C are same. It's given, time is same. The time is equal for both of them. So just equate that and you'll get the answer. So D into mu is constant. So therefore D1 or dA mu A will be equal to dB mu B. Therefore, I can write this as mu B divided by mu A will be nothing but mu B divided by mu A will be nothing but dA divided by dB. The thickness of the slab's ratio is given as 6:4. So this will be 6 divided by 4, correct? 6 divided by 4 is nothing but 3/2. And mu B by mu A is nothing but what? It is mu over here, A comes here, B comes over here. Remember 1 mu 2 was mu 2 by mu 1. So A mu B will be mu B by mu A. This is nothing but refractive index of B with respect to A. B with respect to A. Remember, it's always ulta, it's always reverse. If A mu B is written, it is pronounced as B with respect to A. I just told you this thing. So I think the answer should be 1.5. Got it, my warriors? Yes, the options, this is the option which is correct. Option B is correct, 1.5. Perfecto. Perfecto. Great. Moving on to the next question coming up on your screen. But I think before that, we'll just quickly go through the laws of refraction. The first law is very obvious and it's very straightforward. It's the same as the law of reflection. Okay, come on, let's see how many of you can quickly type the first law of reflection. What was it? Yeah, okay, some of you have made some mistake. What is the first law of reflection, my warriors? Remember, the first law of reflection was that the incident, the refracted and the normal, all three are in the same plane. Remember, planar property. So they are all in the same plane. That means I can also write for coplanarity, I can write incident ray dot refracted ray cross normal ray, unit vectors, doesn't matter what you take, will be 0. This is nothing but your coplanarity test. This works right over here. This is your coplanarity test of vectors. Dot and cross. If 3 vectors are coplanar, if 1, 2, 3, 3 vectors are in the same plane, okay, if they are in the same plane, then their scalar triple product, this is called as the scalar triple product because there are 3 numbers you are multiplying, so triple product, and the dot with the cross, this is called as the scalar triple product. Yep, that's it. Very good. So scalar triple product is always 0. Next, the second law, that's very straightforward, and you might have learned this back in 10th grade. This you can try it out experimentally for different angles, and it turns out that if you measure the angle of incidence and angle of refraction for the same medium for different angles, first this, and every time you measure the r, the ratio of sin I by sin r will always be constant. In fact, that is always going to be mu. So very important law out here. So it says nothing but the ratio sin of I divided by sin of r is the refractive index, so it is 1 mu 2. This is what Snell's law is all about. 1 mu 2. This is medium 1, this is medium 2. So this is what Snell's law is. Sin I by sin r is 1 mu 2. This is very important. Now we are going to extend this property also in a bit. Hold on for that. But before that, let me also remind you, when light goes from dense to rare, it bends away from the normal, but when it goes from rare to dense, it bends towards the normal. I'll repeat why this happens. See, I just told you sin of I by sin of r is 1 mu 2. Okay, it's the refractive index. If you're going from rare to dense, the refractive index of this medium with respect to this medium, I'll repeat, when you're going from rare to dense, the refractive index of this medium with respect to this medium will be more than 1. So wouldn't this ratio be more than 1? Understood? Because this is dense, this is rare. So relatively, this medium with respect to this is higher density. So the refractive index is more than 1. So sin I by sin r is more than 1. Therefore, I is more than r. You can clearly see I is more than r. Fair enough. In this case, if you apply the same logic, sin I by sin r is equal to 1 mu 2. In this case, the refractive index of this medium, rare medium, with respect to this medium, this is dense, this is less dense, this is rare, this will be less than 1. The medium's refractive index with respect to this is less. So refractive index is less than 1 relative. So hence I is less than r. It bends away from the normal. This bends towards the normal. Got it? Perfect. There is only one situation when light does not refract. What is that situation? Quickly type it out in the chat box. Okay. Fine, Prakash. I will definitely consider your suggestion, bacha. Alright, think about it. There is only one situation when light does not refract. Light does not refract. What is that situation? There is only one situation when light does not refract. What is that? If you have any medium 1, medium 2, and if this is the normal, and it so happens that the light rays are traveling along the normal, then whatever is incident will just go as it is into the other medium, and this is basically perpendicular to your surface. The light ray is basically perpendicular to your surface. This is your light. And in this case, the angle of incidence is 0, and so is the angle of refraction. A lot of people think angle of incidence is 90 degree. Nah, angle of incidence is 0 degree. Okay, yes, perfect. It should be along the normal. Yep. No, it's not critical angle. It is when it is incident exactly perpendicular to the surface, basically along the normal. So angle of incidence is 0. So then there is no refraction. No refraction which occurs. Refraction means bending of light. If there is no bending of light, then there is no refraction. That will only happen at normal incidence. Okay, so this is also called as normal incidence. Normal incidence. All right, perfecto. Let's start solving some questions maybe coming up on your screen, and here it is. No, Munir, that is a different thing. That is basically light will get reflected. So what I meant to say, Munir, the light goes from one medium to the other medium but still doesn't bend. That will only happen at one angle, and that is 0 degrees. When we talk about critical angle, light does not go from one medium to the other. It comes back into the same medium. Then it is no longer refracting at all. Okay, there is no refraction which is happening at all. Okay, it's just coming back into the same medium. Oh, yes. Incident angle is 0 degrees. Yep. That critical angle, total internal reflection is different concept. Let's come to that in a bit. Hold on for that. Okay, look at this problem. A ray of light is incident at an angle I from some dense to rare, rare to dense probably, and reflected and the refracted rays are mutually perpendicular to each other. The angle of reflection and the angle of refraction are respectively R and I think something is missing, but it's okay, it's not needed, you can assume it. Then the incident angle will be, okay, read it carefully and think about it. Yes, Monica, thank you so much. My health is perfectly fine. I tested COVID negative just last week or so, and my entire family was positive few weeks back, like 2-3 weeks back. That's when you know I was on the smaller screen, and now all of us are negative and doing fine. Thank you so much for all your wishes. Tamil, I was born in Tamil Nadu. I was born in Salem. All right. So that's why I like a lot of idli sambar and puri idli and masala dosa, vadai, everything. Yes, I like all of that. Maybe just because I was born in Tamil Nadu. I don't know. All right. So Ankit saying A. Let's figure this out. There we go. So it's clearly mentioned in the question. The reflected is this one. This is reflected. And the refracted. This is the refracted. Okay, this is the reflected and the refracted. They are mutually perpendicular. It is clearly mentioned in the question. This is 90 degrees. Fair enough. Now, when will this happen? Let's figure this out. First of all, if this is R prime, let me start marking some angles and you will start seeing some interesting thing. If this is R prime, this entire angle is 90. So obviously this angle is 90 minus R dash. This is 90 minus R dash. Got it? Fair enough. Similarly, oh, I don't even need to do that. Sorry guys, just one second. Let me start from here actually. That will be better. Yep. If this is R, this will be 90 minus R. If this is R, this is 90 minus R because this entire angle is 90 degrees. Now this angle is 90. So if this angle is 90, obviously this angle will be R because again complementary of that. If this is R, how much will this angle be? This will be 90 minus R. That angle will be 90 minus R. So this is angle of refraction. This is angle of incidence. So by Snell's law, what will you get? Think about it. You will get sine of I divided by sine of whatever that angle of refraction is. Sine of 90 minus R is equal to mu. But wait a minute. This R and this I are basically equal because it's getting reflected. I is equal to R. Did you forget it? Remember this law of reflection? So this will be nothing but sine of I divided by sine of 90 minus I. Sine of 90 minus I, it's nothing but cos of I. That's trigonometry, complementary angles, right? So sine by cos is nothing but tan. So tan of I is equal to mu. Therefore, I is equal to tan inverse of mu, which is option A, I believe. Yes, it is correct. Very good. Excellent. 45 degrees, no, it's not 45 degrees. In fact, 45 degrees is not even in the answer. You can see that. Now this is very important result. This is a very important problem because this will come in Brewster's law. This will come in Brewster's law. Okay, and if you remember Brewster's law, do you remember Brewster's law? Light waves, polarization. Do you remember that topic? Do you remember the topic? Pradeep, I wish I knew Tamil, man. Then for sure I would have done V-Master lectures for physics. Hello Dakshin, join in bacha. I think you guys are late. Remember, in that particular topic of, polarization, I had mentioned about this, that if you have unpolarized light, which is incident on some surface, then you will see that if the refracted and the reflected light are at 90 degrees, then this light is basically going to be polarized in nature. This was your Brewster's law, if you remember it correctly, and that happens exactly at this angle. Tan of I is equal to mu. Okay, very, very important. So that's why this problem is significant. Yes, the polarizing angle or Brewster's angle, correct. So the light which is unpolarized, when it falls at this angle and the refracted and reflected rays are perpendicular, only then this light rays are completely polarized. Otherwise, it is partially polarized. It is not completely polarized. This is why this problem was so important. Perfecto. Moving on to the next question coming up on your screen. Wow, what do we have? There is a ray of light and it falls on the surface of a spherical glass paper weight making an angle alpha with the normal and is refracted in the medium at an angle beta. Okay, the angle of deviation of the emergent ray from the direction of the incident ray. Well, if you have forgotten or you do not know what is Brewster's angle, I would request you to please go to Pathfinder playlist, watch the lecture number 2 or 1, I think one of them is on polarization. Just watch that lecture, it's there. I have explained what is polarization, what is Brewster's law, what is that angle at which the light gets polarized, what is the meaning of light getting polarized. All of this I have explained. So just watch it in light waves. It's a part of 12th standard series. It was just done last month, bacha log. Okay, moving on to the next one. Here it is. Try to do this question, but before that, probably we should draw a diagram. Ray of light falls on the surface of a sphere. So sphere is this. It falls on it and it gets refracted by the time it emerges out. This is how it will look. The light ray will fall in and it will emerge out over there. Let us draw the normal so that we can mark the angles very easily. So if this is the center, I believe this should be the normal, something like this. Okay, this is our normal, and I will just draw another normal over here. Fair enough, something like this. Okay, these are your normals. I hope you can see that, my warriors. Perfect. All right. Now what is given? It is incident at an angle. It is incident at an angle alpha with the normal. If this is the normal, this angle is alpha. Good. And it refracts at an angle beta. So with the normal, the angle which is made is beta. Now think the light which is entering here shifted, tilted by some angle, it deviated. Correct? It deviated inside the medium. By the time it reached here, it further deviated by certain angle. Let's find out how much does it deviate at this and this place. Then I can find the total deviation, the angle of deviation. So the net deviation will be deviation at first point plus deviation at the second point. Now think, what is the deviation at the first point? Then we'll go to the second point later on. See, if I continue that ray, over here like this, okay, if I continue that ray, you will see the light has bent by certain angle over here. This is delta 1. Can you now quickly guess what is this delta 1, my warriors? Think about it. What do you think is this delta 1? Just by simple plain geometry of angles. Very good, Ankit. Mod of I minus R. But here I know I is more than R. So alpha minus beta. can you see if this is alpha, then this entire angle is also alpha. Opposite angles, alpha, alpha. So what is delta 1, my warriors? Delta 1 is nothing but alpha minus beta. I hope that is very, very easily seen over there. Got it? Hello Sidhu Siddharth, welcome aboard. Next, here what I will do is I'll use simple geometry. I'll tell you what. See, isn't this triangle an isosceles triangle? Because this side is equal to this side. You see a nice isosceles triangle, it's radius. So it's an isosceles triangle. So the base angles will be equal. So if this is beta, then this is also beta. If this is beta, this is also beta. Perfect. Now a property of reversibility principle of light. Reversibility principle of light. What is the reversibility principle of light? If light falls at certain angle and it refracts at certain angle, now if you change the direction of light, okay, if you change the direction of the light exactly reverse, it will follow exactly the same path. So if angle of incidence, or rather angle of refraction is made angle of incidence and angle of incidence is made angle of refraction, it's not going to matter at all. Only the arrow marks directions will change. That means if light falls at alpha, it comes in at beta. So if light comes in at beta, it will come out at alpha. Got it? Light comes in at alpha, it refracts at beta. That means if light is incident at beta, it will come out, refract at alpha. That means if light is falling at beta, it should come out. It should come out at what angle, my warriors? It should come out at alpha. Now again the same story. It has deviated by some angle. How much? It's the same story, right? It's the same story here or there. It's one and the same thing. That means, shouldn't this be also alpha minus beta, my warriors? Shouldn't the final answer be 2 times of alpha minus beta then? Hence, where is it? Option B should be correct. Got it? Everyone? This is how it works. Complete symmetry. So what and all properties have we used? We have used Snell's law. We have used deviation. We have also used reversibility principle of light. Not many people know reversibility principle of light has very, very important significance. You don't know how it will come to use in different problems. So this is a very good question for that. Moving on to the next question. All right. Yes, option B is correct. So moving on to another question. Very interesting question. Complete use of geometry. Jones Joy mechanical properties lesson is already over long time back in December only I completed it. Viscosity done, surface tension is done, Young's modulus is done. It's there in the nurture playlist. If you're not able to find it, just go to the past videos, you will get it, and I'll try to put it in the playlist in case it is not there. All right, Jones Joy. Okay, so look at this. There is a person, he is looking through this hole. Okay, a person can see through a hole from the top end of a rod at a height, and the rod which is placed here is of height h. The beaker's height is 3h, the base side length is 2h. Now it's completely empty. When he sees through the hole, just because of this edge, these rays of light are just able to enter his eye, and he can see the top end of a rod. So if you are placing the rod here, you are just able to see the top end of the rod. Now you pour some liquid in it. And the liquid is poured till a height of 2h. Now he is able to see the lower end of the rod. Interesting. Very, very interesting. Let's see what do we do now. Now, question is, what is the refractive index? It's not a straightforward problem. Let me tell you in advance. Let's try to do this. First of all, let's see if I can figure out certain angles maybe, and that might help me in the later part of the problem. Okay, so I'll just draw probably a base like this. If this is h, this is 3h, obviously this much is 2h. This much is 2h. Got it? This is also 2h. This is also 2h. In this triangle that you see, if this is 2h, and this is 90 degree, obviously what is this angle? Quickly, you should be able to tell me. What is this angle? This is 2h, this is 2h, this angle is 90 degree. In a right angle triangle, if the two sides are same, then what will happen? Good evening, Satruti, and wish you a very, very happy birthday. And I hope all your wishes get fulfilled. And stay tuned on this channel till the end so that we can celebrate your success when you crack JEE. So what do you think is the angle? 45 degree. Perfect. So this angle is 45 degrees. Got it? Perfect. Okay, I'll keep this on the side. I think I don't need it anymore. Next thing, when I pour some liquid, okay, so when I pour some liquid, so maybe till the height of how much? 2h. So 2h will be exactly the midpoint of this. So I should draw a line like this. So I poured that liquid till here. And remember, this is 2h, but only this much is h. Okay, only this much is h. This is from bottom till here, it is 2h. Fair enough? Now, think carefully again. This line is exactly in middle of this green line, and if I had drawn a line at the top, think about it. Isn't this line exactly at the midpoint? And this is h, this is h. If this is h, think carefully. If this much is h, shouldn't this much also be h? Perfect. This is also h, and if this is h, and since this is 2h, shouldn't this much part be also h? Got it, my warriors? Got it, my warriors? I have just marked all the distances now. See if you guys can see it. So Durvanak, what just happened? See, earlier, forget the blue ones. The ray of light which was at the top end of a rod, this rod was placed at the end of the beaker. The rays of light were entering here. Okay. This is h, this is 3h. How much is this? 3h minus h, 2h. So this is 2h. This is also 2h. This is 2h, this is 2h. This is a right angled triangle, isosceles. So that is 45. This is also 45. Good. You pour the water till 2h. If you pour the water till 2h, the total height of the beaker is 3h given. So how much is remaining? H. And this, if this is h, obviously this is also h because this total height is given to be 2h. So I hope you understand, this is h, this is also h. Got it? Because this was 2h, this was h, this is h, this is also h, but this is 2h, and if this is h, this is also h. That's how it is. Okay? So you try to figure it out on your own, you will understand it. Alright. Now if this is h and this is 45 degree, so in this right angle, small right angle triangle, you can see this will be also h. And if this is h, this is 2h, this is also h. Lot of geometry, guys. Lot of geometry. Yes, Satruti, you can definitely join Vedantu Bacha. There's a link in the description box. Vedantu Pro subscription. Go ahead, check out that link. You can definitely check out all the courses available. And if you still have doubts, ping me on my Instagram handle. Great. Now, see, what is happening is, when the liquid is filled up to this height, he can see the lower end of the rod, meaning the light rays from here are able to reach the high. So it will look like this. This is the ray of light which is able to reach him. This is the light ray which is getting bent and it is reaching him the second time. Did you guys get it? Perfecto? Perfecto? Excelente. Now I think I should draw a normal so that everything is clear. Okay, so this is our normal. Interesting. And now think, if this is our normal and if this is the light rays, I can take anything as angle of incidence, I can take anything as angle of refraction, because reversibility principle of light. Even if light rays were to go from here, it can reach over here. Reversibility principle. So usually I take incident in the rarer medium and refracted in the denser medium. So let me just stick to that ideology. There is nothing wrong in that. So let's say I call this as I, and let's say I call this as R. Okay, this is I and this is R. Oh, I just saw this. I and 45 will be equal. Did you see why? Look at this yellow dotted line and look at this white line. They are parallel lines. Did you see that? These two are parallel lines, my warriors. And you just saw that this is 45 degrees and this is I. So therefore I will be equal to 45 degrees. You just got that? Perfecto. Now the next thing, R is remaining. So for R, maybe I will look at this right angle triangle. I think that will help me. This right angle triangle, that one that I have drawn over here, which is something like this. The height of the right angle triangle is 2h. The base of that right angle triangle is h. Okay, and this is R, of course. This is R, of course. And this is h, this is 2h. How much will the hypotenuse be? How much will the hypotenuse be? It will be root of h square plus 2h whole square. 2 square is 4, 4 plus 1 is 5. H comes outside, so h root of 5. That is what the hypotenuse is. The hypotenuse of the right angle triangle is. Like, sir, why the hell are you finding out the hypotenuse? What is the need of it? See, the thing is, read the question. Refractive index. Refractive index means mu. Mu means Snell's law. Snell's law means sin I by sin R. Sin means opposite by hypotenuse. Understood the connection? Did you guys get the connection? Refractive index, Snell's law, sin I, sin R. Sin is opposite by hypotenuse. So that's the reason why I have found this out. Understood, my warriors? Perfecto. Let's do this now. Let's see what do we get. So, okay, I just don't want it on that side. Please come over here. I don't know how it comes. I just need to do some dance maybe. All right. Oh, it came. So, what is it? Using Snell's law, mu will be equal to sine of I by sine of R. So this will be sine of 45 degree divided by sine of R. Sine of R opposite by hypotenuse. So that's h divided by h root 5. Sine 45 is 1 by root 2. H cancels, so 1 by root 5. So solve it. Obviously it will become root of 5 divided by 2, which is option B. Done, done, done. Look at the solution. How many lines we took? 1, this is like, okay, 2, 3, 4, okay, nothing. It's hardly anything. This is only the part of the solution. Everything that I have done here is just diagram, geometry. Not many equations are there. Complete logical visualization, geometrical optics. That's it. A lot of geometry, a lot of visualization, very good analytical skills. That's all. Baki sab, everything else is just simple calculation. Got it, my warriors? Uma, I'm not in a new studio. It's the same studio. I've changed so many things. My lights. Oh, look at this. This is how my light is. Oops. Yeah, there you go. That's my light. Yeah, I've changed the lighting positions. So many things have changed just so that you guys get the dark mode. It was a task, trust me on this. I put a lot of carpets out here so that the sound does not echo. And yeah, a lot of things. Trust me on that. Plus Microsoft, PowerPoint, everything. So everything is looking different. It's look like, yeah, it's a new Shreyas sir. Okay, there we go. Tanzim, Arzan, that was a JEE Advanced type of question. Okay, and I took time to explain you. But in the long run, when you have enough practice and when you don't have to explain anyone, obviously you will do it little bit quickly. In fact, you will take 1/3 of the time, because when I talk, I have to explain, I have to make you understand, repeat, etc. So it takes time. Otherwise, if you just give me that question or if you are solving it, you will solve it much faster. Okay, that's what I hope. Okay, great, cool. Okay, now let's move on to internal reflection. Okay, internal reflection is coming next. Look at this animation out here. See if you're able to figure out what we are going to talk about. Hello Astha. No props, Sugun. I'm always there to put a lot of efforts for all of you. Glad you like this, Shankar. So see, here, I don't know whether you realize this, there is some laser light, there is a tube of some dense translucent material. The light which is entering the tube, do you see it is getting reflected at different points where the arrow mark is shown. Usually, when light goes from one medium and there is air or some gas outside, it should come outside of that medium. It should get refracted. But instead, it is following the laws of reflection. So that is internal reflection, total internal reflection. And this is a property only when when the light rays travel from dense to rare. I'll repeat, this property is obeyed only when light rays travel from dense to rare, not from rare to dense. And let's have a look at this using this simple simulator up on your screen. See, here this is an animation where this is angle of incidence, this is angle of refraction, this is medium 1, which is air right now, the medium 2 is glass maybe, and I can change the angle of incidence. Observe. Look at this, how beautiful this is. 30 degrees incidence, 19 degrees refraction. I make it 0. Oh, there is no refraction at all. There is no refraction at all. I increase the angle of incidence. You can see the refracted ray is at a much smaller angle. I can increase it more, and there you go. You might be wondering, sir, wait a minute. I can see one more line. Faint, but it is there. 55 degree. What is this? You can see this is incident. This is refracted, but you can see this also. What is that, guy, my warriors? What is that? If this is your incident ray, this is your incident ray, and this is your refracted ray. Can you see that? This is your reflected ray. This is your reflected ray. And always the angle of incidence will be equal to angle of refraction. That's what it is. And always the sine of whatever, incident 55 divided by sine of 33.1, this will be your mu. Okay, I hope that is something which you are able to see. Now, imagine I increase the refractive index of this material. See what happens. The light bends even more. Diamond and many dense materials, translucent materials, they have very high refractive index. The light bends more over here. So that's what happens. If I make the refractive index as 1, there is no bending at all, because air, 1, 1. Light ray will go as it is. Only when the refractive index changes, that's when the light rays bend. Got it, my warriors? Perfecto. Excelente. Reflected rat. Yes, Shyam. Reflected rat, for sure. You take rats, throw it on the wall. I don't know. Are rats elastic or inelastic? I have not tried that. It will be fun. Taking rats, throwing them on the wall. Will the rats stick or will they not stick? I don't know whether they are sticky or non-sticky. You should tell me that. I have not thrown rats in my life. Alright. So next, N1. If I change this now, this is going to be interesting. Okay, this is going to be interesting. Let's see this. Let's say I make this as 1 point, I don't know, something, 1.5 maybe. Okay, 0, 0. Okay, I change this. This is incident, this is refracted, bending away from the normal. Okay, bending away from the normal. Some of the light is also getting reflected. If 100 light was coming, 100 units of light, maybe 90 is going there, 10 is going here. Maybe, I don't know. I increase the angle. Interesting. Light is still coming in, reflecting and refracting. Yes, everything is happening. I increase the angle. Oh, there is a limit. Look at this. There is a limit till which the refracted ray can increase. That's it, done. That's it. It can go only till 90 degree. After that, the light has no other option but just to reflect back. It cannot come out. It's trapped. It's inside that medium. That's the reason why I said this internal reflection can only happen when light is trying to go from dense to rare and not from rare to dense. Is that understood, my warriors? Yes, Chalakuti critical angle. Oops, why is it called Chalakuti? What is the meaning of Chalakuti? Is it something? I don't know. Okay, so here it follows laws of reflection. You can see beautiful. It's like a mirror. You'll be like, oh my God, is this a mirror or what? But no, it's not a mirror. And here you can see it refracts, here it reflects. So a lot of people think total internal reflection is a very special thing. Now, why does that name come and all of that? See guys, reflection was always happening. Reflection was always happening over here. But only when the angle of incidence is beyond a particular limit, then only reflection occurs. That is why it is called totally internal reflection. Total internal reflection. Okay, so that happens only when the angle of incidence reaches that critical angle, and that's what we're going to talk about. Okay, so there we go. Critical angle. Can I draw? Yes. Okay, so I'll just draw it right over here. This is the normal. Okay, This is how the light rays are going to come. Okay, this is your critical angle theta c. This is 90 degrees. This is basically your refracted ray. This is your refracted ray. Remember, this will be your dense medium. This will be your rare medium. Rare medium, generally 1, dense medium, mu. Okay, mu is the refractive index of the dense medium. So, if I write Snell's law, I will write sine of theta c divided by sine of 90 degrees. This is at critical angle, will be equal to, think about it, should I write mu or should I write 1 by mu? This is the challenging part. Many students will make a mistake. Should I write mu or should I write 1 by mu? Think carefully. Oh, Chalakuti is dear sir. Okay. Oh, there comes our Chalakuti critical angle. I like that word, Chalakuti. It's nice. I'm going to use that word very often. Okay. So, interesting. So, is this going to be mu or 1 by mu? Think about it. Hi Tarshan, welcome bacha. It's going to be 1 by mu because you're going from dense to rare. If you're going from rare to dense, it would be mu. This is 1 by mu. So sine 90 is 1. So sine theta c is 1 by mu and therefore theta c will be sine inverse of 1 by mu. Is that clear, my warriors? Yes. Very good. Very good. So this is your Chalakuti critical formula. Okay. So this is your Chalakuti critical formula. Remember this. Perfecto. Moving on to the next one. Coming up on your screen. 1 by meow. Yes, 1 by meow. Very good. It's not mu, it's meow. Oh my god. Naneshwar. Yes. Great. And remember guys, these are very important symbols. This is called as meow. Okay, this is called as meow. This is called as bow bow because this is like dog, right? This D actually stands for dog. Okay, so what does a dog do? Bow bow. So that's how it is. So keep all these things, symbols in mind. Many students think that this symbol is delta. It is not delta, it is bow bow. Keep this in. This is meow. Very good, very good. Keep it up, keep it up. So moving on, and here is the question coming up on your screen. When a ray is refracted from one medium to the other, the wavelength changes from 6000 to 4000 Armstrong. The critical angle for the interface will be, the critical angle will be how much? Think. Okay. So wavelength has changed. Wavelength has changed from one to other. When wavelength changes, when medium changes. And I think I mentioned about this. See, to find the critical angle of the interface, I need critical angle means that Chalapati critical angle, our dear critical angle. What was the formula? Sine of that theta critical angle was 1 by mu. I need mu. So how do I get mu? Mu, refractive index, will be the speed of light in, air upon speed of light in that particular medium. So it will be C divided by V. I just given you that formula. Speed of light, I can write it as frequency into wavelength in air upon frequency into wavelength in that particular medium. Wavelength changes, frequency is same. So it will be wavelength of air upon wavelength of medium, frequency gets cancelled. Wavelength is 6000 divided by 4000. Interesting, 6 by 4 is nothing but 3 by 2, correct? So I just got mu as 3 by 2, put it over here, so it will become 2 by 3, that is nothing but sine theta c. So our Chalapati critical angle will be how much? Sine inverse of 2 by 3. So that's our Chalapati critical angle. Where is it? Sine inverse 2 by 3? Yes, it is there as option C. Perfecto. Moving on. Excellent. Option C should be correct. Yeah, it is. Got it? Perfecto. Okay, so it's a dear one. It's a very dear and near one for me, the critical angle. Okay, so moving on to the next one. Now this is a brilliant question. Many people are going to lose minutes, tens of it to solve this problem. But I'm going to teach you an easy trick to solve this. Observe first. A ray of light is incident at the glass water interface. at an angle I, it finally emerges parallelly to the surface of the water. Then the value of the refractive index of the glass is, and remember, water's refractive index is given, refracted angle in water is not given to us. Oh, Chalapati. Oh shit. I made it as Chalapati. Okay, it was Chalakuti. What's Chalapati then? No, Chalakuti was dear one and Chalapati is, oh my god, I need to be really careful. Okay, especially when you don't know the language, it can mean something else then. And I don't know. I don't want to be held responsible. Okay, so see, interesting things over here. You want to find mu g. You don't know r. You will start writing equations. Like, for example, you can see this is 90 degree. So you will apply Snell's law at this point. So at this point, you will apply Snell's law. You will apply Snell's law. And from Snell's law, you will try to find out r. Correct? Because I is 90, r is unknown, mu is given. Once you get r, this r and this r are alternate angles, so they are same. And then again at this point, you will apply Snell's law. And then again after applying Snell's law, okay, interesting, I will get the value of mu g, because the value of mu g has to be found in terms of I. I is given, mu g you can find it out. Okay, that's how it is. Okay, thank God. Thank God, Astrophil. Okay, great. This is a long procedure. I don't like it. What I will do, I'll do something which is very, very easy. Okay, let's just get rid of all these things. I don't like this. This is the lengthy method. This is the government method. So you go to the government office. So that's what happens usually, right? You go to one person, then go to the second person, then go to the third person, just to get some damn, approval, or I don't know, just to get some information. So that's what it is. It's a very, very slow procedure. Instead, I'll give you a simple trick, and remember this trick, I'm giving you the proof of that, but you're not going to sit and do it in the exam. I'm just giving it to you over here so that you can use it in the exam. Look at this. If you have multiple layers, this is refractive index 1, this is refractive index 2, this is refractive index 3, and so on and so forth. Many such layers are there. Light falls, okay, from medium 1, okay, light falls from medium 1 at an angle of I1. Then it gets refracted and it makes angle I2 over here. You can use any symbol, I or R, it really doesn't matter. It's just a symbol for angle. This will be also I2. Then it goes into other medium. Let's say this is I3. So obviously this will be also I3 and so on and so forth. Then this will be I4 and so on and so forth. Okay, medium 1, 2, 3, 4. So many mediums are there. If you apply Snell's law over here, what will you get? You will get sine of I1 upon sine of I2 will be, it's going from 1 to 2, so 1 mu 2, and 1 mu 2 I had already mentioned, it is mu 2 divided by mu 1, correct? Cross multiply, you will get mu 1 sine I1 will be equal to mu 2 sine I2, correct? Mu 1 sine I1 is mu 2 sine I2. That means if I apply the same procedure here, so I will say similarly. So similarly, what can I get? Over here, I will get mu 2 sine of I2 will be mu 3 sine of I3. And I will also get mu 3 sine of I3 is equal to mu 4 sine of I4, and so on and so forth. I'll continuously get this. That means in general, what can I say? In general, when you have layers, okay, when you have layers, you can just say mu into sine of I is a constant. It's just a constant. So this trick will help you out very, very easily to solve the problem. Okay, this is the proof of that. All right. So I don't want to probably erase this, so maybe I'll just use a different color for this question. See what I'm going to do. I just have to use the fact mu into sine I is constant. You can do it for any medium. So how about taking this air medium and just directly the glass, forget the water. It really doesn't matter. Just forget the water. Just mu into sine I is constant, no matter which medium you take. So mu for air, and directly for glass, if you apply it, what will happen? Mu for air is 1. Sine of 90 degree will be equal to mu for glass is mu g. Glass angle of incidence is I. So sine 90 is 1. So 1 is equal to mu g into sine of I. Therefore, mu g will be 1 divided by sine of I. That's it. That's the answer. Done, done, done. Is it there somewhere? Option B. Done, done, done. What is the meaning by constant ratio? Meaning that when you change the different angles for that given pair, you will always see that the ratio of their signs is constant. That's the meaning of the constant ratio. In this case, here it is constant because you can see mu1 sin I1 is mu2 sin I2, which is also mu3 sin I3, which is equal to mu4 sin I4. So any mu into the respective angle of respective sign of the angle of incident or refraction will be a constant. The product will be constant. That's all. Okay, very good, excellent. Understood, my warriors? Perfecto, perfecto. This is such a brilliant question, and that's the reason why we took this up. Yes, I think this was just done. Yes, this is already done. Okay, now moving on to the next one. A diver at depth of 12 meters sees the sky in the cone of a semi-vertex angle. This is such a brilliant question. Many people don't know this about something called as the fish eye effect. You might have heard about the fish eye filter, maybe via Instagram or Snapchat, but what is this fish eye effect? See, I don't know whether you know this. If you're underwater or if there is a fish, probably it cannot see everything around it which is in the air. Yes, Shyam, very true. And I'll tell you why this happens. Let's just draw a very beautiful scenario. This is water, and let's just say we have a fish, maybe or here. Okay, so this is our fish. This is how a fish looks like. This is how I learned this in my school back in 1st grade. All right, great, cool. That's the fish. Now, imagine things which are outside. Okay, they are going, the rays of light which are outside, which they are going to, change the medium when they are going to enter water. You can also look at it the other way. The rays of light coming out of the fish will go outside at different angles. You can either go from out to in or in to out. Doesn't matter. Reversibility principle of light. So the ray of light which will come out like this will just go like that. Okay, normal incidence. So the ray of light will just pass like that. This is normal incidence. There is no refraction at all which is happening. Rays of light which will go like this will bend away from the normal. The rays of light which are going like this will bend away from the normal. The rays of light which are coming like this will bend even more away from the normal. There comes a point where you see, okay, I'll just probably just draw this surface, that the angle of incidence reaches the critical angle and the right ray is no longer able to refract. The light ray is no longer able to refract because you have reached the critical angle. The refracted ray will make 90 degrees with the normal. So there comes a critical situation, and I'll just draw that critical situation right over here. Look at this. The light ray has reached here. The refracted ray will be almost 90 degrees. So the only thing that can happen is reflection. So there is total internal reflection happening over here. There is no longer any kind of refraction which is happening, only reflection which is happening. So all the rays which will be entering here will just be getting reflected. That's it. That means I think I have, where did it go? Oh my God. I only have a particular region over the surface of water through which the light rays can go out or they can enter in. Do you see that, my warriors? The light rays which are coming in or which are going out are only in this circular region. All the other rays which are beyond this circular patch will only get internally reflected. That also means if there was light ray which was coming here, it will not be able to reach the fish. Understood, my warriors? Yes, something very fishy. This is what was fishy about it. Oh, Sham, you learned it in UKG. Oh my God, kids these days, They learn how to draw fish in UKG. Oh my god, I was late. I learned how to draw fish in first standard. And elephants in second standard. Yeah, you want to see how I draw elephant? Oh, you don't. Trust me, you don't. Forget it. Alright. So, that's how it looks. Understood? Great. Now that you understand this, it becomes very easy to solve. Let's draw, please. Okay, there we go. So let's draw this. First of all, the diver is at a depth of 12 meters from the water, sees the sky in a cone. So that means, oh, by the way, do you see this is a cone which is formed? This is a cone. There is a semicone angle which is formed. So I'm just going to draw this, and I know that this angle over here will be the critical angle, correct? This is the critical angle. This is the maximum extent till which you can see. Beyond that, you cannot see. I hope this is clear. Okay, so we are talking about that maximum critical angle over here. If this is theta c, this is also theta c. Perfect. And this is basically 12 meters. This is where your diver is. This is basically your surface. This is your surface. Okay, the light ray will be 90 degrees over here. Perfect. I know the critical angles formula. Sine theta c is 1 by mu. Remember your Chalakuti critical angles formula? It was 1 by mu. Done, 1 by mu. What is mu? It is 4 by 3. So 4 by 3 will become 3 by 4. So basically, your theta c Chalakuti angle will be sine inverse of 3 by 4. Where is it? It is here. Option C. Done. C for Chalakuti. C for correct answer. Perfect. And C for Capto. And C for cool. Got it, my lovely warriors. Understood, my lovely army. Very good. Perfecto. And be like, sir, what is the use of 12 meters? It's of no use. Yeah, just ignore. Just ignore. It's not needed. It was not needed in this question. But this concept is very interesting. That a fish can only see only in this particular patch. Beyond this, all the rays are just getting internally reflected. Interesting. Moving ahead to the next one. Another beautiful question coming up on your screen. You all would have again and again seen this application back in your 10th grade, and probably if you have already started studying term 2 in your CBSE, maybe in your school, that optical fibers make use of the fact of total internal reflection, and the light rays which are inside the optical fiber, they just keep on getting internally reflected. Now, and this is the diagram. Look at this. The optical fiber, the light rays are getting internally reflected. I used to always wonder, why does it get internally reflected? Always. What if the light rays by mistake comes at an angle which is not the critical angle, it is less than the critical angle, then the light ray will go out. The light ray will go out. And then I will see that as the light rays travel inside that medium, slowly, some places, the angle might be more than the critical angle, and slowly the light rays will exit out, and the optical fiber is of no use because light rays escaping. I used to wonder about this until I found this question which was asked in JEE probably in the 1970s. And this is what the question is. Beautiful question. Okay, let's look at it. Light enters at an angle of incidence in a transparent rod of refractive index n, mu, whatever you want to call it, for what value of refractive index of the material? Read it, it's very interesting. The light which once enters does not leave it throughout the surface whatsoever be the angle of incidence. This is the solution to the problem I faced. But now it's a new problem, okay, because you have to solve it. Okay, so what is it? No matter how you incident it, the light ray is never going to come out, so you decide that critical refractive index. Above that, if it is there, you don't have to worry about it. You just can sleep peacefully because you know that light ray is just going to get internally reflected whatsoever is the angle. No, it's not about the radius. Let's draw it and let's think what must be happening. See, imagine a light ray which just falls like this. It will go like that. There is no problem for this light ray. It's just going to continue going like that if it is falling perpendicular to the surface. Fair enough, nothing great about it. Let's say I choose some other angle. Let's say I make the light fall at this angle. Now, if the light is falling at this angle, the light is going to bend towards the normal and the light is going to hit here, and here you can see this is the angle of incidence from the dense to the rare medium. Because one thing is for sure, if the light comes out over here, then it's gone. But one thing is for sure again, if it gets reflected, think about it, by chance the ray gets reflected, then for sure it will always get reflected everywhere, because this angle will be this angle, this angle will be this angle, this angle will be this angle. So if you prevent the reflection here, you prevent the reflection everywhere else. Do you guys agree or disagree? Put it up in the chat box. Got it? Got it, my warriors? Perfecto. So let's just get rid of this. Now there is some critical angle. Okay, great. And then I'm just going to choose some another ray, maybe something like this. Okay, let's just make the ray come out like that. And then it hits here, because now this will be the new refracted angle. If this is your angle of incidence, this will be your refracted angle. And now it will hit here. And now this is another angle of incidence. Okay, this is another angle of incidence, some new angle of incidence. I can bend this ray even further. I'll choose another color maybe. And it goes like this. Okay, this is your angle of incidence. Now the light will bend probably here. This is your normal, and this is your angle of incidence. Now think about it carefully. Will you be worried about the red, blue or green ray? Factually speaking, think carefully, logically speaking, will you be worried about the red ray, blue ray or green ray for it to get reflected inside? Think logically. Will you be worried about the red ray, blue ray or the green ray so that it gets internally reflected, so that you don't have to worry about other rays? I feel, see, look at this. Green ray, okay, I'll ask you a simpler question. Among red, blue and green, these three eyes, which angle is the largest? Come on, put it up in the chat box. Red, blue and green. Which eye is the largest? Quickly put it up in the chat box, my warriors. Only then you will understand this. Which of those eyes are the largest? Among this eye, then this eye and this eye. Alright, which of these eyes are largest? Obviously the green eye. Can you see that? It's making a larger angle, smaller, smaller. As it comes here, the angle becomes smaller. Here the angle becomes larger, here the angle becomes smaller. So this eye is obviously less and this is the largest. Agreed? Now, do you remember light rays, if they are going from dense to rare, they get internally reflected if the angle of incidence is more than the critical angle. When does TIR occur? When the angle of incidence is more than the critical angle. Now, out of these three, this has the largest angle. So, meaning that there is a good chance that the green ray will be getting internally reflected. Good chance it will be getting internally reflected because it has a big angle. So, good chance it will be just getting reflected. Also, it means one more thing. If red is getting internally reflected, I'll repeat, if red ray is getting internally reflected, for sure, 100% guaranteed, no negotiations out here. For sure, blue and green will also be getting internally reflected. Agree or disagree? Because eye has the smallest angle of incidence. And if that ray only is getting internally reflected, for sure the rays which are incident at larger angles will be getting internally reflected. Do you guys agree with this? Understood, my warriors? Hence, I can say, if the red eye is totally internally reflected, then I can say the other angles or the other rays are also totally internally reflected. So the critical case is the red one. The critical case is the red one. Understood, my warrior? Such a beautiful concept. We have not written any equations till now. It's not needed as of now. Now I'll do the next part. What is this angle? See, the maximum angle. What is this angle? What is this red angle? It's almost tending towards. What is this angle? Think about it. What is this angle? This angle is almost tending towards 90 degree. Agree? Disagree? Agreed, right? If this is I, think about it, this is also I. And if this is I, then obviously this angle is 90 minus I. Got it? Apply Snell's law over here. See, what do you get? So using Snell's law, I will get sine of 90 degrees upon sine of refracted angle, which is 90 minus I, is equal to mu, of course, right? Mu, refractive index. Sin I by sin R is mu. Now, sine 90 is 1. Sine 90 minus I is cos of I is equal to mu. Okay, interesting. I'll not do much over here. Now, what is cos of I? Oh my God, I don't know that. But I know one thing. This I will be the critical angle because if red is getting totally internally reflected, this is the most important statement over here. If red is getting totally internally reflected, that means this red eye is the critical angle. Get it? Red angle is the critical angle. Everybody getting this, my warriors? Let me know in the chat box. So basically this sine of I is 1 by mu. See if you follow this till this point. See if you follow this till this point. Everybody agrees? Now if I know sine of I can easily find cos of I. That's what I need over here. If I know sine of I know cos of I. How do I find cos of I? Cos of I is nothing but root of 1 minus sine square I, which is nothing but root over 1 minus 1 by mu square, which is nothing but root of mu square minus 1 divided by mu. Correct? That's what I'll get. So put that over here and let's see what do we get. So 1 by cos I, that means 1 by root of mu square minus 1 divided by mu is equal to mu. So when this mu goes on the top and okay, nothing is there over here, is equal to mu into root of mu square minus 1. This mu and this mu will get cancelled. So square both sides. So 1 is equal to mu square minus 1. So 1 plus 1 is 2 is equal to mu square. So therefore mu is equal to root of 2. That's our final answer. So the refractive index should be more than 2. If the refractive index is more than 1.414, and no matter what you do, you can dance in front of all the gods if you want, but that ray will get internally reflected. That's what it is. Okay, you cannot negotiate. It will get internally reflected because you have considered the extreme case, largest angle. This ray falls at a very small angle. If that ray only is getting internally reflected, no chance the other rays can get out of this. It will get internally reflected. That's what the situation tells us. Got it? Did you love this question? And if you're loving all these questions, I hope you're smashing the like button. Okay, so moving on to some more questions now. But before that, remember all the annotations, the entire problems, theory, everything will be available to you in the Telegram channel. The link is there in the description box. If you have not joined the new Telegram channel, please join that really fast, okay? Or else you'll miss all the updates. Okay, so Astrophiles, this is a marathon session, so maybe around 2 hours, okay? Last few concepts remaining, apparent height and apparent depth. I'm going to give you the formulas quickly now. So when you see the sun, moon, anything else, wherever you see it, it's not actually there. And the reason for that is because of the bending of light. So the rays of light coming from the sun or any body, Jupiter, Mars, anything, they bend through the atmosphere. Reason being, atmosphere itself has a small refractive index, and that's the reason why you perceive it at some other point. So this phenomena occurs even in other things, like you place a coin in water, you see that the coin and the bottom surface is on the top, the apparent depth is shallower than the actual depth. Apparent means what you perceive, what you feel. Okay, that's what you feel, what you perceive. But that's not the truth. The truth is actually the bottom surface of the beaker is much deeper than what it is perceived to be. That's what it is. All right. So all this happens because of refraction of light. The light rays bend, and that's the reason why you perceive it closer. And the reverse is also true. The reverse is also true. When you are inside a dense medium, you will find objects in the rare medium are farther away. Okay, look at this ray diagram. This makes things very, very obvious. This girl is seeing this diver. This diver is actually here, but the rays of light bend. So she feels that the diver is here. That's the problem. Do you see that? The rays bend away from the normal. That's why she feels the diver is more on the top, shallower. This is actually deeper. Same thing. When the diver sees the girl, the rays of the light which are going, they will bend towards the normal. So when you project it backwards, the girl is seen here. That's what has happened. So I'll mark all the things so that you get a hang of it. Okay, so probably let's say this is H actual, and this, let's say I'll call it H apparent. Then the formula goes like this: the apparent height is mu times of the actual height. This formula will be used when the observer is in denser medium. Keep this in mind. Observer is in denser medium. Similarly, this thing over here, okay, this is actual depth, but what you are seeing over here is the apparent depth. So when the observer is in rarer medium, then the formula changes slightly. Then, oops, not H, I have to use D. Then the apparent depth is the actual depth divided by mu. Not multiplied by, divided by, because apparent will be small. So you divide it by a number more than 1. Got it? Okay, will you remember this formula? So when you are in denser medium, when you look outside, you will feel it is far away, taller. So you expand. How do you expand? Multiplied by a number more than 1. When you are outside, rare medium, when you see things which are inside water or glass, they appear closer. So to make it closer, divided by mu. As simple as that. Got it? Shall we go ahead? Moving ahead to the next question. Coming up on your screen. A transparent cube of 15 centimeter edge contains a small air bubble. Its apparent depth when seen from this side is 6. Apparent depth when seen from the opposite side is 4. Then the refractive index of the material of the cube is. Very interesting phenomena. You can even apply this in real life. See, the actual bubble is somewhere here. This distance, let's say, is D1 actually, and this distance is D2. But when you observe the bubble from this side, okay, when you observe the bubble from this side, it is perceived over here. And when you observe the bubble from this side, okay, when you observe the bubble from this side, it is perceived to be here. It feels shallower. So what is given to us? From one side it is 6 and from the other side it is 4. So from one side this is 6 centimeters and from the other side this is 4 centimeters. What is D1 and D2? It is very obvious. Think carefully. What will be D1? D1 is actual depth. This is apparent depth. These are depths. So can I not say, my warriors, let me just write it over here. Okay. Can I not say apparent depth 4 is actual depth divided by mu? So therefore, can I not say D1 is equal to 4 mu? Similarly, from there, apparent depth 6 is actual depth d2 divided by mu. So therefore d2 is equal to 6 mu. But d1 and d2, both of them together, what is the total edge length? It is 15 centimeter. So d1 plus d2, isn't it 15 centimeter? Just substitute the values. So 4 mu plus 6 mu is equal to 15. 4 plus 6, 10. 10 mu is equal to 15. Mu is 15 by 10, which is 1.5. Is it there somewhere? Yes, option D is correct. Got it? Very straightforward. Shall we move ahead, my warriors? Straightforward question. So that's how you use the concept of apparent depth. Next question. Oh, it's the same thing. I think it's just got repeated again. Okay. Refraction through glass slabs. Very important topic. And that's what we're going to see now. So when light falls on a glass slab, you will see it gets refracted. But since the edges are parallel, by the time it comes out, you will see that this angle or this final emergent ray and the incident ray, they both are parallel, no matter how you turn it. Very, very important. Yes, 15 centimeter is the total length, Kamal Raj. And it so happens like this. Let me just show it to you over here. Okay. So if you draw a normal and if you measure, this is the angle of incidence, this will be angle of refraction. You draw another normal. This is R. This is also going to be R. By reversibility, if this is R, this will be I. So that's why this incident, this is incident, this is called as the emergent. This emergent is parallel to the incident. Deviation wise, deviation. What is the net deviation? The light ray bends and again bends on the other side. So the rays are parallel. The net deviation is 0 degrees. There is no deviation. But there is one interesting thing which happens. The light ray was going like this. Because of the slab, it has now been shifted. It has now been shifted. So this distance that you see over here, this distance that you see over here, this is called as the lateral shift. What is this called? This is called as the lateral shift. It's the amount by which the light ray gets shifted. That's what it is. So you need to keep these terminologies and these concepts and this diagram in mind. That's why I put up real images so that you know how things work. Alright, and I'm pretty sure you would have done this experiment back in school. So this is a ray diagram. It looks scary, but it's the same thing. It's just that I have marked everything over here for your notes. So the incident and the emergent rays are same. I just told you about it. And when you calculate the lateral displacement, this is what it turns out to be. T sine I minus R by cos R. Very important formula that you should know. There is no negotiation in that. So you cannot say, sir, I will not remember this. Remember this formula. It's very simple. You can derive it also easily using simple geometry. It's not that difficult as well. So the amount of lateral shift that occurs will be T by cos R into sine of I minus R. You can try this out as homework. Very, very easy. Trust me, very, very simple formula it is. I'll tell you, I'll give you a hint also. Okay, this is a hint. Take these two triangles and it will be done. Take one triangle like this. Take one triangle like this. This is one triangle that you need to take. This is a right angle triangle. And the other triangle that you need to take for solving this is this one. Take this triangle. So there is one side which is common, which will help you. You can see this side is common. So just try out these two triangles. Apply some trigonometric ratios. You will get this side because exactly you need this. This is what you need. Okay, so I've given you the hint. Try it out at home. I hope you can solve this at home. Agree? Disagree? Let me know in a chat box by putting up a thumbs up. Now, one more thing. Okay, see, when you have a glass slab, let me just put it over here. Very important. When you have a glass slab, and let's say you are the observer here. Let's say the thickness of the glass slab is T. We have just seen apparent depth, apparent shift, right? We have seen that. So is it the thickness of the slab? No, it is not the thickness of the slab. Oh, this T? Yes, this T is the thickness of the slab. Yes, Oh, that T is the thickness of the slab. Correct. Yep. Yes, astrophile. Now, one more thing which you need to remember about glass slabs. See, whatever topic we do it in detail. I'm not going to leave anything, okay? Is that if you have a point here, let's say O, it will appear over here as O1. This is actual, this is apparent. That means anything behind it will also be shifted. So if I have some point like A over here, this is actual, I will find that point over here at A prime, A1, whatever you want to call it, this will be the apparent position. This is the amount by which it has been shifted. So a glass slab shifts everything, the entire world behind it, by some amount. So that shift can be easily found. That shift can be easily found. And I'll tell you what it is. See, it's very easy. This is T, right? So how much will this be? Think, this is T apparent. This is T apparent. So in order to find that shift, O1, it is nothing but T minus T apparent. This is the apparent depth. This is the actual depth. When you see from here, the actual depth, and this is the apparent depth. So O prime will be T minus T apparent. And T apparent is nothing but T by mu. I just told you about it. So this will be nothing but T common 1 minus 1 by mu. So the entire world behind you shifts by an amount of thickness of the slab into 1 minus 1 by mu. This is a very, very important formula again. T into 1 minus 1 by mu. All formulas are important. Whatever it is, I am giving it to you. Yep. Is it clear? Yes. Afaf, yes, I do remember you, bacha. Good evening and welcome aboard. Hello, Scarfall. Yep. So, I hope this is clear. All these formulas are important. Let's solve this question coming up on your screen. Based on the glass slab concept, the observer is here. Two slabs are present. There is a point P. The question is, the image of P will be formed at a point when you are seeing it from the top. Where do you think it will be formed? Okay, how far will it be from that point? Look at this. Options are measured everywhere from the point P. Will it be above? Will it be below? Okay, one thing is for sure. If you take a glass slab and you are the observer here, the entire world behind you will be shifted closer. The entire world shifts closer to you. Remember that? So if the entire world shifts closer to you, point P will be shifted above. That means some options naturally get eliminated. It should be above, it should be above. Below is obviously wrong. It should be above. Okay? Option C can never be correct. Perfect. So how much will it shift by? That is simple. The shift, the amount by which the net shift. How do I calculate the net shift? It's very simple. The net shift will be, okay, due to each slab. And what is the shift formula? I just gave you. The shift formula is thickness into 1 minus 1 by mu. Right? I just gave it to you. So the net shift will be thickness. Thickness is 1.5 into 1 minus 1 by mu. Mu is also 1.5. And the best part is both the slabs are same. Mu is also 1.5. Thickness is also 1.5. Do you see that? Thickness of the slabs are same. So the shift will happen twice because, you know, both slabs are same. Both the slabs are same. That's the reason why I can do this. So let's do the math. 1.5, that's 3 by 2. 1 minus 1.5. 1.5 is 3 by 2. So this will become 2 by 3. So this will become 3 by 2. 1 minus 2 by 3 is 1 by 3. 3. Yep. So just check this out. 1 minus 2 by 3. Oh, I forgot that 2 into 2. Into 2. Yes. So this will just become 1 centimeter. Is 1 centimeter there somewhere? Yes. It is there. 1 centimeter above. So that's option D. Very good. Very good. Very good. What a beautiful question. Moving ahead to the next one. Option D was correct. Wow. This is amazing question, guys. Motion of objects and there is a surface in between. Let's solve this question. There is a fish which is going up. There is a bird which is coming down. the fish which is rising up towards the surface with the speed of 3 observes a bird diving vertically down towards it with a speed of 9. The actual velocity of the bird is how much? Very interesting question. Okay, let's try to solve this. Fish is moving. Let's see how much is the fish moving with. The fish is moving upwards with a speed of 3 meters per second. So the speed of the fish is 3 meters per second. Bird, I don't know what's the speed like, but let's just assume that the speed of the bird is VB. Now here is the problem. The question says the fish observes the bird moving vertically down, relative. This 9 meters per second is relative speed with respect to an observer in water. And water is basically a denser medium. Water is basically a denser medium. Now, when you are in a denser medium, what happens? When you are in a denser medium, what happens? Think. Whatever you see on the top is seen little bit far away. Correct? Whatever you see is seen little bit far away. The apparent height is more than the actual height. So, can I say the apparent height of the bird, okay, of the bird, this is apparent, is mu times the actual height of the bird, right? This is how it works. Now, if I just divide this or differentiate this with respect to time, just think about it. I just differentiate this with respect to time. What do I get? I will get the velocity of the bird, rate of change of distance is velocity, which is apparent. This is the apparent, what is perceived. And this will be equal to mu times derivative of the height of the bird actually, velocity of that particular bird, but this is actual. Now, this entire problem is all about perception. What is it being felt like? The fish perceives the bird coming towards it with a speed of 9. But don't forget, the fish is also moving with a speed of 3 meters per second. Agree? Disagree? So, can I not say, my warriors, the relative speed of approach, okay, can I not say this 9 meters per second, is it not bird speed plus the fish's speed? Bird speed and the fish's speed, both, it's like two trucks, two cars moving towards each other. What is the relative speed? This speed, V1 plus V2. V1 plus V2. That means 9 meters per second will be the perceived speed of the bird, which will be mu into velocity of that bird, okay, which is actual, okay. This is your perceived speed plus the speed of the fish. What is the speed of the fish? It is 3. So, mu, I think we have to take it as 4 by 3, I suppose. So, because it's water, right? It's water, so water's refractive index is 1.33. So, into velocity of the bird, which is actual. This 3 goes on the other side, so it will become 9 minus 3. This is 6. 6 is equal to 4 by 3 into velocity of the bird, which is actual. This 4, this 6, this will be 2, this will be 3. 3 3s are 9. So, this will be 9 by 2 is equal to velocity of the bird. That's it. That's what I got. And this is actual one. 9 by 2 is 4.5. Is 4.5 there somewhere? Yes, it is option A. The entire game was all about perception. So what we did was, the fish, when it sees the bird, the bird's perceived speed itself will be different. So I calculated the perceived speed first. The perceived speed will be mu times the actual speed. That's it. And once I get the perceived speed of the bird, I have to add the fish's velocity also, because even the fish is moving. So hence, the relative speed, net speed will be V1 plus V2. That's why I have put a plus, because they are approaching. So whenever they approach, it gets added. Okay, is that clear? Perfecto. Have energy for one more problem. Last problem coming up on your screen. Yep, I know we have stretched the lecture a bit, but yes, last problem coming up on your screen. I hope you are reading it right now. Ray optics is a big chapter, robbery gaming, big chapter. We have at least 1, 2, 3 classes at least, yeah. Savarish, you can leave a comment after the session, I'll definitely answer it. Okay, consider the situation shown in the figure. The water, refractive index is given, is filled with a beaker up to a height of 10 centimeter. A plane mirror is fixed at a height. This is the plane mirror. And distance of the image from the mirror after the reflection from it of an object O at the bottom. O is at the bottom. Interesting. Let's do this question. See, what is happening? This is a mirror. The mirror is facing downwards. There is water inside, there is an object here. When the mirror sees the object, it won't see it here. This is the actual position of the object. But what the mirror will see, because you are in the rarer medium, this is the rarer medium, what the mirror will see is this object somewhere over here. This will be the apparent position. This will be the apparent position. So I think the first thing you need to do is figure out how much is this height, how much is this much height, and that is very easy to find out, trust me. So that will be nothing but remember actual divided by mu, and actual is nothing but 10 and mu is nothing but 4 by 3, I suppose. Yes, so by 4 by 3, so it will become 3/4 of 10. So it will become 3 by 4 of 10, over here. Perfecto. Now, once I get this, this is anyways 7.5 centimeters. This is 7.5 centimeters, right? What will the mirror do? Whatever it is seeing here, it is going to reflect it back. So whatever is this distance, understand, whatever is this distance, at the same distance it's going to reflect back and it's going to form the final image over here. This is the final image over here, and this distance will be exactly equal to this distance because it is reflection, complete plane surface reflection. Now how much is that distance? That's very simple. I hope you can see that. That distance will be nothing but 5 plus this. It will be 5 plus 7.5, which is 12.5 centimeters. This distance and this distance are equal. This much is 5. This much I just calculated it to be 7.5. 7.5 plus 5, it's 12.5. That's the answer. Got it? From which months we need to prepare for JEE 2023? Swiss, you should have started preparing back in 2021 itself. Usually target 2023 students start preparing from the month of April or May, maximum by June. But if you have not yet started preparing, it's really high time you buck up and start preparing yourself. If you need help, Vedantu already has 11 standard crash courses. Go and enroll yourself. There are links in the description box. Already you are very late, but time is not lost. You can still catch up. So if you want to catch up, there are courses in Vedantu. Okay, Swiss. Yep, that's the answer. 12.5. This is the same repetition. The first question for homework, just put it up in the comment section after the session is over. This is your second question for homework, and this is your third question, I believe. Yeah, this is your third question. Okay, so just put all the answers in the comment section, and remember, if you want to also complete the syllabus for JEE 2022, that's 11th and 12th both, then we have the 90 session crash course for physics, chemistry, maths together with test series, 10 full and 10 part. Obviously assignments, recordings, notes, PDFs, strategy sessions, tip sessions, my sessions are also going to be there. I'm also going to enter into the crash course, and also you can compare your scores with AIRs, previous AIRs, so that you get a realistic feeling of the mock test. If you're wondering how much is the course price, it's 20,000, but there is 50% off on it, so you get it for 10,000. But since you're watching the video, I give you this discount coupon of SHHPRO, from which you get 10% additional off, and you get it for 9,000 rupees, is roughly 100 rupees or less for each class. So it's quite affordable. Go ahead, check it out. And I hope you, and where do you find this course link. It's there in the description box below. So go ahead, smash that link, open it up, you will see the course page. Thank you very much for joining in, tuning in. It was indeed lovely. We have solved so many questions on plane surface refraction alone. Next lecture will be on curved surface refraction, and after that we are going to go to lens combination and all of that, and then we are going to go to prisms, one more class for that, and then probably, you know, optical instruments and all of that. All right, so that's it for today. Thank you very much. Take care, stay safe, stay well, and also have a great dinner. I hope you all prosper and do well in the upcoming examinations. So stay tuned for more lectures. So hit the subscribe and smash the like button if you have not done it yet. That's it from my side. This was your Capto Shreyas going live from Bangalore. Hasta la vista. Bye bye.